Hey guys, welcome to lesson 512, day 2. It's really just a continuation of what we talked about yesterday. So first let's go ahead and review finding the inverse of a function. We're going to do that process where we come up with a list of steps to describe the original function and then work backwards from that list to create a new list and use that to create our mathematical inverse. So when we are looking at a function like this, it's a little bit involved. It's not just 2 steps like a lot of the ones we were doing before. So let's start our original list. Okay, the first thing you see when you're looking at this, you start at the x and you think, okay, what am I doing to the x first before anything else? All right, and here you should notice that before any of these other operations are applied, we are first subtracting 1. So I'm going to say that my first step is to subtract 1. Okay, and then once I take care of that step, I will notice that the next thing that happens is that this whole thing gets squared. So I'm going to write that we square. Okay, notice how like this whole thing is in parentheses and that was the x minus 1 thing, so that's how I know that that's the next step. Okay, and then step 3, once I square it, I am left with multiplying by 2 and adding 5. So this is where order is really, really important. You got to remember that in your order of operations, multiplication always comes before addition. So my next step is going to be to multiply by 2. Okay, and then my last step then will be to add 5. Okay, and that is pretty much it. I have covered all of my steps in this function. I have written down all the things that happen to this x in the correct order. So now I need to go and follow my list backwards, starting with adding 5, and do all opposite operations. So I'm going to match colors as well. So instead of adding 5, remember we have to start at the bottom of our list, we are going to subtract 5. Step 2 will be going up from there, and instead of multiplying by 2, we have to divide by 2, because that's the opposite of multiplication. Okay, and then we are moving on to the next one. This step right over here is saying to square, and the opposite of squaring is to square root. Okay, and then finally, I have one last step to go, and that original one says to subtract 1, so now I am going to add 1 because adding is the opposite of subtracting. All right, and now that I have made my list of directions, I am ready to create my inverse function. That's the notation for it. So remember, I like to just write my floating x there because everything we do happens to the x. So now that I've written my x, I can start. So first I have to subtract 5, so I'll put a minus 5. Next, I have to divide by 2. So let's just put all of this over 2. The next step is to square root. So I'm going to square root everything I have here so far. So it's going to look like that. And then I have to add 1. So that adding 1 is going to happen outside of my square root. Notice how the square root ends here. And that's because I'm adding 1 to that whole thing that we already had. Right, and that's it. This is my inverse function of this original equation. So anytime I ask you to find the inverse, you can do this process. Come up with your first list, your second list, and use that second list to make your function. All right. Next, we are going to go over how to recognize if tables are inverses of each other. So remember that the main thing you want to look for with inverse tables is a flip-flop of x and y values. So you have to be careful here because not every set of tables will always happen in the same order. So like I know what we've been seeing so far is like a direct flip-flop of like each level. but things can show up in different orders. It doesn't really matter technically on the table, so you just have to watch out for that. So let's just take a look at this point by point. It has to work for all of the points. So let's look at this one, -1, 1. So if we have, okay, that's a bad color choice. If we have this point, we know that on an inverse table, this point would turn into a flip-flopped version, which means the 1 would come here and the -1 would come here. So we need to find this point on this table. Sure enough, it's right there. So we're good on that. So let's do another one. 2, 3. So 2, 3 would turn into 3, 2 because we just flipped the numbers. And so we need to find a 3, 2 on this table. In this case, at an x value of 3, it goes with 3. So this doesn't quite work, right? It needed to be 3, 2. So that right there is enough information to prove to us that these are not inverses. But let's just look a little bit more just for fun. So this 0, 4 would need to turn into 4, 0. And this is the one that has a 4 in the right spot, but this is not a 0, so that doesn't work. More proof that it's not inverses. And one more, 5, 7 here. 5, 7 should turn into 7, 5 on the inverse table, but here it has a 7 in the right spot, but this should be a 5. So that tells us that they are not inverses. All right. Okay, let's do another example. So here we have another table pair. So let's do the same thing we did before. So the first point is 1, 0. So we know that we need to look for a 0, 1 in the inverse table. Notice this is what I was talking about before, how this ended up going here. We found a 0, 1. Okay, and then notice how it's like in the second spot instead of the first spot. That's okay. It won't always be in like the same order. That's all right. Don't rule it out just because of that. All right, and next we have 2, 2. This one, because the numbers are the same, there's not much flip-flopping to happen. So 2, 2 just stays as 2, 2. And sure enough, we have one of those. Okay. Next, I'm trying to follow my color scheme from before. All right, we got a 3, 4. 3, 4 would turn into 4, 3 in the inverse table, and we have a 4, 3 here. Okay, that's good news. And one more point, we have 4, 6 here. 4, 6 should turn into 6, 4, because again, we're just flip-flopping these numbers, and sure enough, here's a 6, 4. And we've used up all of the points on these tables. So these are indeed inverses. Okay. All right, so again, just you want to make sure that every single pair on the original table is represented in the inverse table as a flipped version. All right, so let's move on and take a look at some graphs. So we want to figure out if these graphs are inverses of each other, the red versus the blue, based on this line of symmetry. And now remember that whenever we're talking about inverse graphs, the line of symmetry that we're referring to is this one right over here. And it's always the equation of y equals x, okay? This is y equals x. Notice how it's like always in the same spot. Right through the middle, like diagonal of your graph. So this first one, if you look at this red and blue, this green line does not nicely go through the middle of these. So the red and blue are not mirror images of each other across this green line. It has to be across the green line. So since we did not find the symmetry that we are looking for, we will say that they are not inverses. And the reason is that because there's no symmetry across the line y equals x. Okay, so let's try this next one. We see that here's my green line, y equals x. And in this one, you can see that the red and the blue graphs are actually perfectly symmetrical across this line, right? They are perfect mirror images of each other. So in this case, we can say that they are inverses. Okay, because they have that symmetry. And then this one, we can look again for that symmetry, and sure enough, they are perfectly symmetrical. So we will say that these are inverses as well. Okay, and again, I can't stress enough that you always want to look for symmetry about this line. Like you can literally graph this line in your calculator, just type x into that y equals area and look for it there. All right, one last problem here. Are these two tables inverses of each other? So we have to do that process we just did on the last page, which was to figure out if every single point had a pair that was like opposite. So this is the supposed inverse table. So let's check it out. 1, -1 should turn into -1, 1, right? Because we have to flip them. And there is a -1, 1 here, so we're good. 3, -5 should turn into -5, 3, and it does, so we're good. 5, -9 should turn into -9, 5, so there is one here, so that's good news. 0, 1 should turn into 1, 0, and there's one right here, so we got a match. -2, 5 should turn into 5, -2, and there's one right here. -4, 9 should turn into 9, -4, and sure enough, that is the last point. I know this looks a little obnoxious, but you guys watched me make these lines, so maybe it's not so bad. Okay, that was bad. Okay, so we managed to find a swapped version of each point on this table in this table, so they are inverses. Okay. So the reason we know this is because all points on the inverse table are flipped versions of the first table. I will say of the original table. All right, so we're going to go ahead and graph these. So I'm going to graph my first one in red and my second one in blue. Okay, I'm going to pause the recording while I do that just so I don't waste time. All right, so I have graphed my tables. This red line is this first table and the blue line is the inverse second table. So now we want to check to see if they are inverses of each other. So remember that when we are trying to check for inverses, we have to draw that line of y equals x. So that line is right through the middle here. Oop. Let's try that again. All right. So here is my y equals x line. So checking for symmetry here, we can see that the blue and red are clearly mirror images of each other. If we flipped them, they would overlap right on the other one perfectly. So we can say that they are inverses of each other. And the reason for that is that there is symmetry across the line y equals x. Because remember, this is the line y equals x. Okay, that is all for today. Give the practice problems a try.